let's very quickly go over the things that we discussed. That two types of logic. One is the combinational logic, is where you have so anything which is not register is the combinational logic. Usually these adders and the pattern decoder here and the sorter here, they all are combinational logic. Sequential logic is basically where you physically store. And why do you want to store? Because there is a state of something which you want to store, or the memory that you are storing, to use those values in the next cycle or in the next iteration. And then we discussed about developing. So this is the code that I have generated. This is called a tab delay line or window of values. Usually any machine learning that you are applying for prediction would work on the most current value that you have just acquired, which is at t, and then this is t minus 1. And so you need to keep all these values to do the prediction. And then this is the last value, and after this value will go out. And if it is a linear predictor, and then you have all these coefficients that you multiply and generate a value that will be your predicted value. So module will be like this, and sequential will be something which is, we also call a tab delay line. So it's like a delay line where every time you sample a new value will get into this register, and then the previous value, previous, and the previous, and then the value will get out. So if you are developing a hardware which could do linear prediction of something, and where you are just sampling and samples are getting into your tab delay line, and or if you may also want to have an enable signal, that whenever you want to sample a new value, you assert enable. Once you assert enable, tab delay line would work, and every register will get updated from the newer value, and the oldest value will get out. So enable is also important. As we're going to generate code for the tab delay line, and then it is very simple to generate code for the multipliers. So there is a series of multipliers, and this is usually an adder tree where you have to add product of all these values together to get the final prediction. So this is not really an adder, rather it is an adder tree. So you can have from your breakdown perspective, you have one that you generate a tab delay line, then you may have like part of the same module, all these multipliers and the adder tree, or you can have the adder tree as a function or a task. So so we said it's important that once given a problem, how you break the problem down. Mostly we will be doing this because we will take an algorithm and see that how we can divide it into sub-modules, and every sub-module into leaf modules. And then the leaf modules are something that we develop. We put them together into bigger blocks and bigger blocks and bigger blocks, and then we put everything in a top module. But sometimes you may already have developed some of these, and then you just keep combining them, and you go bottom up. So we covered these things, but I emphasize this a lot from code generation perspective. For generative AI, you got to really critically think to split your design into number of modules, and the split should be in a manner that you can just generate RTL Verilog code, uh, generate its stimulus, test it, validate it, verify it. And it is always a good practice that the partitioning should be done in a manner where end of the module should have a register, a physical register, series of registers, or a memory. Why it is important? Because once you go to the second phase where you go to synthesize and meet the timing, you want to run this whole thing at a certain clock. So then every module you can give a target, that your module, because your module shall assume that all the inputs to the module are coming from another module where all the values are registered. So once we say a clock is always a register to register delay. Okay. So you say, I am giving you a target to run your module at 500 megahertz. I'm giving you a target to run at 500 megahertz, 500 megahertz. So everybody meeting a target means the entire design is meeting the target. So this is the second important thing, that once you are splitting your design, you got to be cautious of only two things. One is, where is my functionality? The functionality is the cloud. Okay. And where is my functionality, which I write using high level of abstraction and use generative AI tool. First, I generate the same logic in Python. And once I'm happy with the Python code, because usually uh, all these generative tool do a very good job, about 97-98% accurately they generate Python code. So the logic is not going to change. So this cloud logic, if you generate Python code in a manner that you kind of are using the same functionality into your Verilog code, so that piece of code will not change a lot. Okay, like we saw in case of sorting, like same loops. We saw the same loops in the uh, in in the Verilog code as well. So you say, okay, and you can always ask Python, instead of using functions, generate the low level code so that you can see that how that specific functionality is implemented in Python, and then you take that functionality into Verilog code. So please remember that the output of your partitioning should be such that outputs are always values are always stored in a register. You don't intentionally, another important thing, don't force yourself to intentionally put registers in your module so that your outputs are stored. They should be part of the architecture. So always, you are never ever going to insert registers in your code so that you meet the timing, because you cannot just go and insert registers. It's because they have implication. If the algorithm assumes the same value to be used by the computation which are happening here, a register would add a delay. So a register would make the algorithm to use the previous value. So everything will be changed and you will not get correct results. Please remember, a register is an algorithmic, is usually an algorithmic entity which is making a piece of functionality to use previous values of your results. If this is not what you mean, then adding register is not that simple. And especially if it is a feedback, a loop is very, very complex. Or if even you are delaying, then you got to make sure that you delay every every path that goes from input to output. Okay, so we will learn about these things. That first we would try to use the algorithmic registers, that algorithm that is using those values, like we have just seen in the uh, uh, we have just seen in our design on the SHA-256, that there's a series of register, then you are doing some computation. Okay, so there is a series of register A, B, C, D, E, F, G, and then after doing this A, B, C, D, E, F, G, you are putting values in another set of register, or the same register A, B, C, D, E, F, G. And then you are again using, so if you want to really make them pipeline, I mean, to have like many of the iteration, let's say all the 32-bit iteration, you unroll them. So you are going to basically replicate this logic 32 times. Why would ever you do this? Because you say, once it is done with processing a block, I pass the value to this series of registers, and now automatically output is always saved in A, B, C, D, E, F, G, H register, always saved in A, B, C, D, E, F, G register, always saved in A, G. So you unroll the entire iterations, all the entire number of iterations of SHA-256, whereas one iteration take 132-bit value, and there are 64 of these values. So you have 64 of these processing elements, and you design it once, and then you place them 64 times. And but the good thing is, every clock cycle you can process one block. So every clock cycle you get a new block. The previous block goes here, the previous to previous goes here. So it's just keep on shifting, and your throughput would be one block, one complete block in a cycle. So every cycle you have a block. This is if you are independently processing a block. But if it is the book which has so many words, then every block uses uh, uh, the value. The next block uses the hash of the previous block to compute. So you cannot just replicate these blocks. These can only be replicated if you have independent blocks. Let's say you are doing digital transformation at Higher Education Commission of Pakistan, where every university, every transaction they are making, every results they are printing, every transcript they are generating, their attendance, their everything, every transaction at every university gets to Higher Education Commission of Pakistan with a digital signature. So what here you have this type of an architecture where you take a block, which is the that you have to compute the hash of the transaction, and you put it through a pipeline like this. So every time you have a new block, a new block, a new block, and you can now imagine that how fast you can do this processing, because now you are exploiting the parallelism by ensuring. Otherwise, there is no point in replicating it 64 times, because if you are the next value requires the the use of uh, output of one block, you got to wait. You cannot put the new block unless you spend all these 64 times. So this block works, then it is sitting idle, pass the result to this block. This block works, then pass it to this block is idle. So last time this block is working, so you're out of 64, only one block is working, because you need the result of the 64th iteration to start the 65th iteration on a new block. So it does not make any sense. So these are the kind of things we will be learning. Then when unrolling an algorithm makes sense, and when we should not unroll an algorithm, rather we just one loop of the algorithm, we convert them into silicon and reuse it 64 times to get to the final result. So hardware utilization is important, and we need to make sure that we are 100% using our hardware and it is not sitting idle, because we don't want to waste area. So this is something that we talk about, that Verilog, there is a module, it has inputs, it has outputs, there is a functionality, and then there are two ways that you define a module and the input outputs. One is that all the ports, you just name them here and then define which out of them are inputs and which are outputs. And the other is, once you are doing it, right away you just tell the simulator that these are the inputs and these are the outputs. So two ways, this is the preferred way, and that we should do it like this. And you can always go, and this I would really highly recommend you to go to the generative AI tool and ask them to generate a hypothetical module for you, or you can ask them to generate a module which should do this, okay, whatever you want it to do, and see that how the Gemini generates, how the Copilot generates, how the Meta.ai generates the code, and how the ChatGPT generates code for your module. So we will try to give you like small exercises where you would take this and ask the generative AI to generate a module for you, so that you can see that how good a module it generates. Sometime uh, uh, they they may, some of them are not very good in generating the correct. Everyone will generate registered transfer level Verilog, but sometimes there may be errors, and that is something which you need to figure out. Then we said structural HDL is where you have already defined gates in Verilog. These are the called gate level primitives, and a synthesis tool will convert your code to the gate level primitives. But you yourself never ever try to instantiate a gate level primitive yourself, because we don't want to uh, code our design at this level, and that is not really required. We are never ever going to do this. Okay, so we covered this, and we saw this is very cumbersome. You have to first draw the circuit and then you do the design. I don't I would rather hate doing this. I want to design my hardware at a high level of abstraction, which is behavior level, where the code should look like a code in Python. So this is just the main thing, that I want my code to look like as the code looks in Python, so that I can understand it, that this is the functionality it is doing. But I got to be cautious about the registers, because registers play a very important role in architecture. So they are algorithmic register, but they are the storage elements. They are to be instantiated where there is no concept of registers, so to say, in Python. So in Python, because there is no such concept, and that concept is the main concept we need to learn, that what is the value of register in hardware. Otherwise, like Python is as good as Verilog almost, but not really, because that would make a big combinational cloud, and which would take forever to actually do the execution or the completion. So level of abstraction is going to be like Python, but because it's a register transfer level, so register transfer, we need to learn that from how from one set of registers the values are going to the other set of registers. So never we are going to do, though this operators are also behavioral Verilog, but never we are going to code something to this level, because you never code actually unless these are the logical operator. We don't code things in Python like this. Okay, you know, don't need to figure out how a sum. You don't want to make truth tables and find out how sum and carry out of an adder would look like. So we would use, if we are going to use an operator, we use an assign statement. This is called continuous assignment statement. It starts with the keyword assign, and then you can write an expression like you write in Python, which is you are adding two numbers. Okay, so you can do that, or anything. You can put a delay, but this delay does not have any value, except that once we start looking at the waveforms, it'll just output will be shown after 5 time units of the inputs. So you see, because sometimes it is very cumbersome to understand what your Verilog code is doing, because everything happens at zero simulation time. So if there are 1 million lines of codes, everyone gets executed at zero time of simulation. If you look, all values will change. It'll be very hard for you to understand what change has basically resulted into subsequent changes in your code. So it becomes very cumbersome. So you start getting headache, because if there are 1,000 variables, all will change value at the same time at zero simulation time. And because everything in hardware is happening at the same time, this is the second concept that we need to just ingrain, that in hardware simulation everything happens at zero simulation time. If you want to see the delays, that this and then because of this happened, because of this happened, like in a sequential code, because we are used to seeing things happening sequentially. I have added, now I have divided, now I have shifted, now I have done this, now I have done this. If you want to do that and you want to see them happening in in the sequence of time, you can put a delay in wherever you be seen as a result of this addition, this has happened. So it's up to you, but this has no value once you are synthesizing the code. So this is just for your statics or visual presentation of the results. Once you are seeing the results in the waveform, that you want to see them happening in some sequence of time. So just remember the timing. Okay, so we said low level of abstraction we hate. If I want to see what an adder would do, I will just add number. This is something you don't see in Python as such, and perhaps you see in Python also does this. So it is like you are adding three numbers, and your part of the answer will be in sum, and another part will be in count, and how the part is split depending upon their sizes. So you can actually do that. A plus B plus C in is sum and C out, and that's how we want to write at a high level of abstraction. So behavioral modeling is that definitely we want to synthesize our architecture part. So there are two parts of the design. One is the design yourself, which we usually call your device under test. So this is what you have designed. And this thing requires something where definitely is going to require a lot more efforts than the design itself, which is the testing. So testing is play a very critical role, where you have to give all kinds of inputs and get all kinds of output. It's very different. Software bugs, people can tolerate software bugs, but nobody tolerates a bug in the hardware. Once there was a bug in a Pentium processor, they have to call all the Pentium back. And that bug was so rare to happen. It was in some very high precision division that Pentium would generate an error. So please remember that nobody expect a bug that you leave in hardware, that you are adding numbers and you're getting a wrong answer. People don't care mostly about a bug in software. Softwares are really buggy, and that's why we see software crashes. And there is always an update, and you keep getting updates, but there is no update for the hardware. So the testing plays a very, very critical role, where you have to kind of generate all kinds of test vectors to ensure that all possible conditions are triggered in your design, and there is nothing which is left untouched, though uh, this really is not possible. For example, even if you are adding two 32-bit numbers, so and you want every bit to change, so it is 2 raised to the power 32 into 2 raised to the power 32, and it'll take you forever to just check a simple adder that it is working to your satisfaction. And that makes the verification very challenging, but at the same time very valuable, because there you have to think that how you are going to do the maximum coverage of the code which is written, so that once you tip out, send it to the fab, you it is guaranteed that it will work properly. So we are going to have high level of abstraction the code. For example, this is a multiplexer, and then leave it to the synthesis tool to translate it into gate level primitives, and then to further optimize it, where as we have learned in our logic design courses, there are min terms and max terms, and then you reduce the min terms and max terms complexity reduction and produce a hardware which uses minimum number of gates. We are never ever going to worry about it. We only worry about how to write your functionality at a higher, how to generate, so to say, functionality at a higher level of abstraction. So there is a Verilog code for this part. So here's your design, you do a Verilog model, and the test batch is important. So you do the simulation, and once you are happy, so a lot of time you spend by just simulating, checking, simulating, checking, validating. And once you are happy with all of this, then you say, okay, now I shall send it to the compiler. Compiler, what it does is, so here is the compiler. So here's you send it to the compiler to do synthesis. And once you're doing synthesis, you go to a fab, ask them to give you a technology library. Technology library, what kind of transistor they are using. You must have heard about 6 nanometer versus 7 nanometer versus 9 nanometer versus 30 nanometers. And there are different fabs in the world. And it's like once you're compiling a code, you mention whether you are compiling it on ARM processor or MIPS processor or Intel processor or a digital signal processor, because this high level C or C++ code has to be converted into the assembly language of the processor, the instruction it supports. Precisely the same case is for the hardware, that once you have Verilog code, you need to say how it should be get converted into low level gate level primitives. There may be, uh, for example, there may be like 3 input AND gate or 4 input AND gate in the library. Uh, and so the translator would know that this is all what is available. So it will synthesize the code, generate a netlist, and that netlist will also be a Verilog code. So it'll create a Verilog version of the code for you to take it as a Verilog model, and still you should able to run your test vectors to get this comfort that after your compilation, your system is still working, but it will be very, 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 very slow. Why? Because now it gets translated into very low level, gate level code, and for like perhaps one line of code that you have written in Verilog, it might have generated thousands of lines of code to be validated and verified. So usually you have tests where you have your test benches, a lot of test vectors that you generate, you do the simulation, and then you may look into the waveforms and the text file. And here you are synthesizing your netlist, and you are mostly doing the place and route, and place and route what part of your design should go where. And you can physically, like you're making an architecture, this is where your kitchen is going to be, this is your drying dining, so this is your atrium. So like you do the placement of bigger things. Same is the case in a chip designing, where you are going to put your memories, your RAM, your ALU, your address generator, and then within them there may be smaller module. Where are you going to put your stove? Where are you going to put your sinks? Where you are going to put your towel rack? So like you do once you are designing your house. And so the bigger placement that you're doing, the smaller placement, then smaller, and everything. How do you place that? You want it to be accessible. So something which is called ergonomics, like you want to make sure that the things that you require should be closer to each other, so that uh, you don't spend too much effort. So you're dining, then kitchen, so that the food can directly go to your dining. So you are thinking in terms of the functionality. Kind of same thing happens here as well, that the people who are doing place and route, uh, they give the timing constraints. Primarily, they want to meet the timing that a signal and the data that goes from one set of register to another set of register must not take more than this much time. So obviously they have to place where the data is moving those closer together. But obviously they cannot put everything, enclosure. So you got to then compromise. So this becomes an NP hard problem. NP hard problem means uh, really the amount of complexity which is there in modern day digital design. It is not possible for anybody to do an optimal place and route the best, but you only care about meeting the timing. Anything that meets the timing, you're happy. But once you meet the timing, after the place and route of your design, you're happy, you can send the chip for tip out. Okay, so this generates the net list of which based on the technology, but net list is something that can also be simulated. So this is now we come to again the Verilog. We have two types of variable, broadly speaking. One is the net type of variable, and the other one is this variable data types of variables. So nets are basically kind of the physical interconnect, but they are also kind of physical interconnect. We may say that they are the storage elements, but they are kind of the same. So the most important of the net is a wire. Okay, so wire type of variable. So there is no equivalent of this in Python, but these are not that important. So you got to have a wire. So wire is type of a variable, like it's a wire 7 down to 0 output. So output is a wire type of variable. Okay, this is type of variable where you have some inputs and you calculate these inputs. Sometimes anything uh, that you don't want anybody to change is the wire. So wire assignment can only happen once on a wire. So some input driven, you calculate, and so you drive some value. So a wire type of variable must only appear once on your left hand side, because you cannot assign on wire at two different times. So wire type of variable is where you have only once appearing only once on the left hand side. On the other hand, reg is a type of variable where you can do multiple assignment. You can say a is equal to 3, then you can say is equal to 4, then you can say is equal to 5. So you can, so we'll just keep in this order, we'll keep changing the values. And obviously it is important once you are testing your design. Once you're testing your design, you got to have these values. You got to keep changing values, and keep assigning them different values. So so this is how you kind of generate bits, right? 32-bit A, and this is 7 down to 0 B2. If you don't write it with a single bit, and then comes all the operators. So this is where we say we want to code register transfer level Verilog at higher level of abstraction. Never, never writing um, uh, gate level primitives or usually the operator, but using all these operators which are there in the other programming languages. If you want to add numbers, add. If you want to subtract, you subtract. If you want to multiply, multiply. If you want to divide, you divide. If you want to take the modulo, you take modulo. If you want to take power, you take power. Okay. So many synthesis tool would get confused because they will not have equivalent of divide or modulo or exponent. So there you got to be cautious about these things. Usually There may be some adder in the library and a subtractor and a multiplier in the library. Like for FPGAs, they have these dedicated multiplier, subtractor, adder, but not a divider usually, and not a modulo or a power. And then you got to design or use some IPs for doing this. Okay, so is interestingly, my mouse has gone on the other side. Okay, so I want to keep it. Can you believe this? I'm not seeing my mouse for some reason. Okay, now I see my mouse. Because this is Apple helping each other not to make me. Okay, so I'm just quickly going over these things. Many of you must already be knowing Verilog. If you even don't, you can just go repeat, and all this is available on the internet. So you can always get a lot more than what I'm telling you from the internet. Okay, so here is so there are some other bitwise operator. We know not as inverts all the bits. For example, if you have 1 0 1, it'll invert all the bits to 0 1 0. And operator taking and of every bit. So there is an example you can look by yourself, that here is this number and here is this number, and obviously you are going to get a one here only because both are one. Otherwise, you will have to have a zero. So OR operator is, or they are doing the bitwise XOR operator and XNOR operator. So they work on bit by bit. So the 3 bits, the second number must also have 3 bits. Okay, and then you are doing a bitwise. Take bit of this, take bit of this, and do the ending. Or if you are doing ORing or whatever. So it's a bitwise operator. That is how it works. So reduction operator we have covered last time as well, that they basically AND all the bits together, or NAND all the bits together, or all the bits together, NOR or XOR or XNOR, all the bits together. So this is how you write a reduction operator. Sometimes you want this reduction operator, for example, if you are doing some operation, you want to see whether all the numbers are zeros or not. So you OR them together. Once you OR them together, if all are not zero, you will get one. And sometimes you want to see whether all bits are one. If you want to see, you AND them together, and you use this reduction operator to see all the conditions are met, and you say yes, all the conditions are met. And so so these are we are very familiar with these are correlational operator. If something is greater than or less than or greater than and equal to or less than and equal to. Okay, so usually, but this is a subtractor actually. If you look at this, it says a minus b is greater than 0. So mostly these all are subtractors. Okay, and but if there is a bit which is x or z, so your output will also be x or a z, so it will give you an x. And once you start printing, you will see x x x x x. It means that for some reason some of the bits in your operator they were x or z's. So are the equality operator equal, equal, not equal? So there we all are very familiar with this, except this one, which is case equality operator. And here it will also check, for example, x for x, cn is equal 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 cn. Here though cn is equal to cn, but because of the x in c, there is an x in c. So whenever there is an x in an operator, it will give you answer as an x. Okay, that means though obviously this number is equal to this number, but there is an x, so it will give you an x and x. But if you are using equal equal equal, then it will compare x with x, and that's the difference between these operators. Then there's a logical operators, means if not true, if this is true and this is true, if this is true or this is true. Sometimes people, they this mistake that they just put and. Please remember, once you put and, it is going to and two numbers, because there is no equivalent of this in Python or in other languages. So you forget to write and. which is a logical AND. Logical means that you say this is true and this is true, and but you say and it will still be a valid statement, but it is kind of, what will it do? That it will uh, take the bitwise ending of the two numbers and will give you a result, and you will get a wrong answer. Same is the case with or. This is or. It is a logical operator which checks the the condition which we're checking, two conditions. One of the condition is met, only then it is going to be one. So A in either this is one, a non-zero, or this is non-zero, so you're going to get this one. Okay, and the same if there is an X in it, so you get an X as an answer. And once you print results, you will see X's. X's means that you have done something, some blunder somewhere, uh, and that's why the simulator is confused whether it is one or a zero. And the simulator is confused, you got to go back and check why you are getting X's. Okay, so you have kind of ignored something somewhere, and then after that X, you will see uh, everything will be resulted. I will be resulting into X, 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 because of the reason the simulator, if your input, any bit in your input is X, the simulator will just generate an answer which is X, telling go back, look into this. Or you yourself are forcing some bit to be X, then is a different case. So shift operator, shift left, logical shift right, and if it is arithmetic, means the sign number, negative remains negative, positive remains positive, then you use arithmetic shift on the sign numbers. If it is unsigned number, otherwise, if you are shifting logical, a negative number may result into a positive number. We may look into this as well. Then other conditional operator, this is also is in C, that you have check this bit. If this is like if else statement, if this is true, then output will be A, else output will be B. So this is called the concatenation now. Conditional operator. Concatenation is that you can put two numbers together to make a 6-bit number by just saying this. And replication is you say repeat 3 times this number and make it a 9-bit number, so it will do that. So they are very handy in coding hardware, uh, these two operators. So here you see an example of an assign statement, which is assigning on a Y, which is a wire. This is output by default is a wire, which is saying S is an input. So inputs are always wires. Once you come to the module, we will look into this. So if S is 1, output is D1, otherwise output is D0. So we have seen an example of an assign statement as well, and which is assign is always on a net, and Y is a type of a variable which is a net. You don't have to write wire. If you want to, you can write wire here, wire here, wire here. It will not object to it, but default of Verilog is that every variable, if you don't mention, it is a wire. Okay, so slicing is that you can just slice, and we have already seen the concatenation and assign variable. This is all we have already seen. And local variables, you got to define whether it is variable is of type wire or is of type reg. So this is up to you, that you have to define variables to be wire or reg. Okay, so this is important. Here I have asked Verilog to generate all the operators or most of the operators in my code. So it just by itself generated 244-bit A and B, and then said going to do all these operators, add, subtract, multiply, and, or, XOR, shift. So here is the statement. And now look at this assign statement. Default, all these variables are variable of type wire because you have not written them as reg. So if the variable is of type wire, you got to use assign keyword to assign value on a variable of type wire. So only assign on a variable of type wire, and there must only be one assignment in the entire code to a variable of type wire. You cannot say add is a plus b, then you again say assign add is equal to a plus b plus c. Okay, because everything happens in hardware at zero simulation time. A zero simulation time means that add, and then it will be confused. Okay, and it is up to it does not, all these statements, they don't happen in this order of priority. This is something which you need to remember in Verilog, because hardware, The simulator may execute this first, and then this, then this, then this, then this, or in any which order it may want to. So if all the assignments are on different variables, then you don't care. You don't care because they are being on the all on the left hand side. Okay, definitely if there is an add and you can use add here, a minus b plus add. So but it will do the add will go there, and then you get a subtract. Okay, so means you can use a variable of type var as many times as you want on right hand side, but you cannot on the left hand side. There has to be only one assignment. So this is important. Um, so these are the order of precedence in assigning values to these operators. We also last time discussed instantiation, that you, so we would use the Britishers' way of conquering word by divide and rule. Okay, so we're going to divide this whole thing into 3 modules. We will generate this and this and this, and then make a bigger module and are going to instantiate. We call instantiation of smaller module to make a bigger module. Okay, so connecting module instances we have covered 2 ways. One is that you put a dot operator, write the real name and then what you want that to be, or remember the order in which the ports are, use the same order. So you can, this is where I have generated the code I've shown you last time as well. The accumulators. So every time I have dot clock, dot reset, dot enable, dot. So dot is basically the original name, and then accumulator one is name in this particular instance, in this particular instance. So this is the code that I have generated for this design. It's so simple, really, to just design this. If you do the divide and conquer, you can easily generate the architecture and the Verilog code. Okay, so these are other examples. This is an important slide. I want to show you this is to remember what to be declared as a wire and what should be declared as a register. So the input inside the module, okay, head is always going to be of type wire. Just remember this rule. Head is always going to be wire. So the output getting out of the module has to have has to be defined as a wire. In out on both inside and outside are going to be of type net. The tail could be a variable like a reg. A tail could be a reg. Why a reg? Because here you want to assign it different values. Okay, to test the design, the same variable has to be assigned different value again and again and again and again. So, but once the value comes inside the module, you don't want the module to change this value. Okay, you can assign it on another variable and then you can play with that variable, but not to this actual net, which is driven by somebody who is outside, sitting outside, is saying, check it for me whether it is true for 2 or not, or 5 for value 5 or not, and you go and you make it 6 and then pass it to no, 5 will remain 5. Okay, so same is the case here. You are computing an output, you can just do whatever you want to do with the variable, but once it goes out you don't want the 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 other module to change that variable. In hardware, this is a strict rule that head makes sense is always going to be of type wire and tail will be a type reg. Okay, there's two other important things, like you can always the once we say divide and rule strategy, a divide and rule strategy where you are breaking, that's why the task and functions are important. Divide and rule says that you break your design into smaller parts, and for every part you can define it as a module, but sometimes a logic does not really uh, worthy of a module. It's something functionality which you're repeating again and again. So there you can define that logic as a function or a task. So this is important that they are kind of a module, but they're not really module. Okay, there is a functionality, you group it together, and where you want to replicate it and use it again, you make it into a function like we do in C programming or in Python programming. Or this is something, a task is same as a function, very few differences. Okay, so some of the divide and conquer things will be ported as function or a task, and this will take me right to the architecture that we discussed, where we have those three blocks, which was majority, choice, sigma 0, sigma 1 in the hash function. So we would rather prefer to define all these four as functions. Okay, so function, 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 or even a task. I don't mind if you do this. So where you have repetitive code, where it enhances readability, you can use function or task. Functions will only return one value, only always return. You can function like in C, you can return more than one value by using pointers, but otherwise function will only return one value. Okay, and this is how the function will return a value. So you define a function mult, and these are the inputs. You can have as many inputs as possible, but function output is always going to be one. Whereas task is different, and the task is kind of like you instantiate a module, almost like this. Okay, so here is where you can have multiple outputs into this. So here is an example of a function. You write function, and this is the name of the function, is also name of the variable. So that's a bit confusing in Verilog. That function name of the function is also the output variable, which is a 16-bit number. Okay, so this is the name of the function, but also it is the output, which is a 16-bit number. That's why you write function, what it is returning, a 16-bit number, and this is name of the function. And there could be as many inputs. You are saying to inputs. There could be as many internal. You have like variables, integers. So you are saying if this b is equal to 0, a 0, 0, then you have a loop, then you have if statement, end statement, and then you have end function. And then you are using this inside your code. So this is your function, and name is mult, and here is where you are using the mult function. So this is use of the mult function into the code. So you can do that. Task similarly is uh, you like, this is the module name, this is the task name. Here you have two inputs and one output, and you say output is equal to a plus b and end task. So it is task and task. Usually you have a task is to be used inside a procedural block like initial or always procedural block. So you write this task and then you have end module and you get the value. So here are the differences between functions and tasks. Uh, so there are like execute 0 time, must have at least one input argument. Arguments may not be output, and inputs you are not going to have any, because name of the function itself is an output. Always return a single value. May call another function but not a task. May execute in non-zero. You may have an always within the always statement. You can have timing constructs. May have a 0 or more inputs or outputs. So this is what the difference between. So once you are asking the generative AI to generate a code, you can ask it that this functionality you want in a function, and this functionality you want in a task, and this functionality you want in a module. And that's why we have come up with these numbers. This I already covered that this is how you express a number in Verilog. A tick B0000001. So this is the number of bits, and whether it is binary or you may have hexadecimal, you may have decimal, and you may have octals. Usually we use hexadecimal and binary. These are the only two. And decimal is only once you are just assigning number, because we in hardware we want to see how many number of bits and what each bit is look like. Once you have decimal, it will not tell you what it is. Okay, so in binary here you will have number like this. In hexadecimal, you will have something like FA3, A, B, C, D, E, F, G, H, A, B, C, D. So 0, 1, 2, 3, A is 10, then B, C, D, E, F is 15. So you have from 0 to 15 numbers. This also we covered. It is like a floating signal Z, and usually if you have uh, a shared bus where you want to disconnect one of the devices which are deriving this bus, so you use a tri-state buffer. Parameterized module, we have already covered this as well, that sometimes you want a code to be reusable across your design. So wherever you can make it parameterizable, you make it parameterizable. A local param is something which you cannot change. It will remain 16 for rest of the life of the code. But param is something which is 8, means that you can just go and while instantiating it, you can keep changing its value. Like this hash parameter size is 8. So this we have covered already, like parameter width is 8, and you have this code which is an 8-bit mux. But then if you are instantiating it, there you can say I want it to be a 12-bit mux. So you write hash 12, so it will become a 12-bit mux multiplexer. And this is how two ways that if there are multiple parameters, you name of the parameter with a dot and its number. And so sometimes your code generator will generate a parameterizable code, so you need to know what it is. I've already told you about the timing, that this is not the real time. This is just for easing you out up so that you see one change is affecting another change in your code. So you may want to put a hash number, and it is just, you may say it is 1 nanosecond, but it is just a time unit. So becomes the how to implement sequential logic, which is basically your memory. So mostly you have combinational circuit, which as I mentioned earlier, look like your Python code. So you are very happy because you have coded something in Python that it directly gets translated into this code. But intricacies in the design comes once you start putting the storage element, that this is what you want to store and reuse. Okay, so here the software will convert in. Here the software mindset has to be changed to a hardware mindset, that this is where my physical registers are. So so to me, a hardware designer knows where his or her registers are, where they have placed in the code, in the design, in the architecture. So this is important, right? So for that, you need to have procedural blocks. And in Verilog, there are two procedural blocks. One is called an initial procedural block, and always. Initial is not RTL. It will not synthesize, because in hardware, there is nothing which will only start once and then it will never happen. Hardware, everything that is there will remain there forever, will be running all the time. So initial is only for in the stimulus that you have initial, where you say initialize all these variables to these values, and then so only for stimulus you use initial block. It initial block must not appear. That shows very poor understanding of the hardware if you write an initial block inside your RTL Verilog code. So initial is prohibited, okay, inside your Verilog code. Always is something which will remain there, because this is where it shows things are happening always. So always an initial block represents a procedural block, we say, separate processes. Each block runs simultaneously. So you have, though inside they may be sequentially run, but you may have as many initial and always block as you want. Okay, so you can have as many initial and always block. Preferably, your left hand side, if you're changing the left hand side, they must only appear in your one always block. Otherwise, it'll be very confusing. Right? So, statement inside a process executes sequentially. Always initial blocks cannot be nested. There cannot be an always block inside an always block. Right? So, it is your Verilog code would always look like this. There are some assign statement. Okay, so part of the code is where you are using assigning on variable of type pi. So here you are using assign statement. Okay, here are assign statement. And then your always block, always block, always block, always block, always block, always block. Most of the time, your Verilog code will be nothing but many always block. And these blocks will further be divided into two parts. One is they are inferring combinational logic, and where they are inferring sequential logic. Combinational logic, combinational logic, sequential logic. Okay, sequential logic means that there is a register in that will infer as a register, or combinational logic there is no register. So it's a cloud, input change, your output will change. Okay, there's a cloud, your input change, your output will change. But a sequential, a change will only happen once a clock comes in. Once a pause edge of a clock comes in, or a negative edge of a clock comes in, only then the output value will change. It will definitely, there'll be a cloud which will be waiting, computing something to be stored in the register, but register will only store a value once a pause edge clock comes in. Okay, so that's the difference between uh, the procedural logs implementing. So that's why Verilog is so simple to learn. In the Verilog code, you see nothing. But if it is a stimulus, you will see a lot of initial blocks. Every block will start with begin and end statement. All blocks start executing at zero simulation time. So you don't know which block will execute when. Okay, though they may have been written in a certain order. So sometimes it is mind-boggling to debug the code, because if you have not adhere to very strong guidelines of coding, okay, where you are making sure only one block has assigning on one variable, so you will be confused that what is happening. The fixing will become very difficult. So inside a block, uh, whether it is sequential as a combinational block, actually, the statement happens uh, sequentially, but outside they all gets starts at zero simulation time. All blocks starts at zero simulation time. Okay, so initial blocks are where you are using for initialization, monitoring, and any function that needs to be done only once. There you use initial block. Okay, an initial block usually you use blocking procedural assignment that happens in a sequence. Whereas a sequential block is an always block where you got to specify the pause edge or a nag edge so that it converts into a register. So usually in an always block, you put always ampersand sign, and there is a sensitivity list. And then there is a series of statements. So this is the structure of an always block. And here you see always add. Once you say pause edge or nag edge of a clock, it means it is going to be a register or a flip-flop. So this is a case of a flip-flop, one bit flip-flop. That every pause edge of clock, whatever is D, it at a pause edge will become Q. So there is it's called D flip-flop. So D will become Q. So this is how it is written. A module flop, a clock is input, your D is input, your output is of type reg. Okay, and remember the design rule where we said into a module the input is always going to be a wire. That's why it is a wire. The output, a tail inside the module, could be a wire or a reg. If the assignment you are making is in the always block, then it will be a reg, because you cannot make an assignment inside a procedural block on a wire. So it becomes a reg. So you have a module and an end module, and this is how you write a module. Okay. So this is will infer a register. If you want it a physical register, okay, not the flip-flop, a register, then you increase the width of the input and the output. So here is an 8-bit number that you input to the module, and this is an 8-bit number now. Okay, so this is an 8-bit number resulting into, after a pause edge of clock, it is getting on the output. So this is how you write. Always add, always use, these are called non-blocking procedural assignment. Okay. In a sequential block, you always use non-blocking Okay. So then sometimes once it is a register, you got to reset a register, uh, at, and that's why everywhere there is a reset button. Okay. Even to a laptop, it says reset, a soft reset. And what is a hard reset? You turn it on and off. Okay. Then it is a, so soft reset is where all the register gets reset. So usually you need to make sure in your design wherever there is a register, you must have a resettable register so that somebody wants to do a soft reset, it just initializes. But if you are not keeping a soft reset initializing every register in your design, then you got to give a hard reset, and that sometimes is not good. So soft reset is connected. All the reset lines are connected with a button which says reset, or can we do a soft reset by asserting a signal onto this. So asynchronous reset, asynchronous reset, these are the two types of resets. And if your reset is also in the sensitivity list of always add, pause edge clock or pause edge reset, then whenever you press a reset, whether there is a clock or not, because there's an or, a register will get reset equal to 0. Otherwise, if it is an M, so this is the code that I have generated using ChatGPT. And it's just once enable is asserted, this is what I'm using in my design as well, in this design. So now coming back to this, and I want to now generate RTL Verilog code for the tab delay line. Okay, this whole thing. So I wanted to generate this code after understanding that my design is, so I thought about this and thought about this three parts to my design. This is a adder tree, which is adding many numbers, and these are the multipliers, these are the registers. And I want an input coming to my module, which I am calling it a tab delay line. I want an enable signal coming to my module, and I want a clock coming to my module. And if I want a reset also, where I am not putting a reset because if there is any garbage, it will flush out automatically. But if I want to, I can also have this. And I want maybe the last value as an output. Maybe, it may not be, but depends. So this is, so I asked, went to the uh, chat GPT. First, let me show you the code it has generated. Uh, and then we will, so this is the accumulator one. Yeah, here are the code. Here. So I hope you can see my screen, right? Okay. So I asked ChatGPT to generate uh, a sequentially connected registers so that the input data, this is data in, which is a 16-bit number, shall get into register, data in gets into register 0 gets into register 1 gets into register 2 gets into register 3. And if I assert reset, so it reset all the values. Okay, so I can show you, let's try to generate this code. So we asked chat GPT, and we can try doing it with the other tools as well. generate RTL Verilog code that takes a 16-bit input and stores it in whereas there are four set of registers, namely R0, R1, R2, R3. The value of R0 shall go to R1 and similarly R1 to R2 and R2 to R3. Okay, all these registers shall be resetable registers. Okay, let's see what it does. Memory full. I don't know what memory full is. Let me again instantiate ChatGPT. Somehow it is giving me an error. It is saying memory full हुई हुई है इसकी. That is strange. हाँ, अक्सर पढ़ा. That is amazing. So it's like, as you can see that it has, now whatever we have learned is also here. So let me dissect this code. It's saying its module name is register shift. Okay, good name. So input is a clock. Yes, there has to be a clock. Then input is a reset because I want these registers to be asynchronously resettable register. And then I ask it that there should be a 16-bit input data. It has made all these registers at also output register. We can ask it that these registers must remain internal to the module. So in the second iteration, I'll show you. Even if it is, I don't care, but because we can just change it. So if it is always at pause edge clock or pause edge reset, which is good, begin. If you assert reset, okay, if reset is asserted, then pause it from 0 to 1. If you make it so all these registers should be 0. So good, these are resettable register. Then I ask it that input data should go to R0, R0 should go to R1, R1 should go to R2, R2 should go to R3, which is excellent. And we are using non-blocking procedural assignment. These less than equal to sign means that whenever there is a sequential block which must infer physical register, I should only use non-blocking procedural assignment. So this is good that it has generated this code. Now let me say modify this code. I don't want all my registers to be output. I want to keep them internal to the module, but I want at the output the summation of all the registers. Output the value for summation of all the inputs, all the registers. Okay, so I'm saying add all the values and that should be at the output. So we say, let's see what it generates the code. So as now we can see, this is very good. Now it has taken out all the registers from the output and there's only data in and sum. Okay, and so beautiful that it is adding. I can also, I say, use assign statement, use assign statement to add values so that it happens in the same cycle. For example, I say assign statement को use करें. So that's why perhaps the little understanding of the, though it is also fine, but now I just wanted to show you this is an assign statement. Assign statement is that the sum has to be a wire, so sum is a wire. Why? Because it has not been declared as a register. These are the registers. So we have seen R0, R1, R2, R3, all are the registers that we have. Okay, so now it's a combination. That's what I was explaining to you. That's a combination of sum R0, R1, R2, R3. Always are, this is looks fine, this looks fine. Okay, now you can ask it to generate. This is perfect. Now generate a stimulus that checks the working of the design for different input values and reset conditions. Okay, now it will generate a stimulus for this. So the stimulus has no input and output, as it is just checking the design, but most of the thing which are going as an input to the module, they are defined as a reg, because you are going to change clock, reset, and this. And things that are coming out of the module, the head, because coming out of the module has to be a Y. So this is perfect. You got to instantiate this. This is also perfect. It has been instantiated. Now it is using an initial block. Initial block only gets executed one, and it must not appear in our RTL Verilog code. It must only see the stimulus. So I'm happy to look at this. And this is clock is 0, and it is generating forever statement, which we will just study. That forever is the every 10 time unit clock is 0, make it 1, 10 time unit clock 1, clock 0, clock 0, clock 1. So it every 10 time unit it is going to flip the clock to make it look like a clock. Perfect. And a monitor we will study is something, if any value changes in the input, it will print out. So monitor is also an interesting statement in Verilog, where you just write it once in an initial block, and it will remain active throughout its life. And when anything changes in the list, which is whether it is your in data or your R0, R1, R2, R3, or whatever, any data sum, it will print those values. And here it is just changing in data, in data, in data, in data, reset, reset. So this is how it has actually generated the code. Now I can even ask it, I want to implement a linear predictor where I also pass four inputs B0, B1, B2, and B3. For it's better I write 16-bit inputs. Let's say 16-bit inputs. This as coefficients of a linear predictor. These values get multiplied with respectively with registers R0, R0, R1, R2, R3. The sum now is the dot product of the coefficients and the uh, values in the registers. Okay. Now I am moving it to make it uh, into a linear predictor. Wow, beautiful. So we see that now I have four further inputs. Now I have actually exactly I have implemented this. Okay. So I have actually implemented this. So step by step, first I tried making a tab delay line. It was working. Then I just added. I did not put all these multipliers. It was working. And then I said, okay. And so this is how you plan to generate your hardware. Though you can, in a single statement, you can do that. But perhaps, just go slow by slow, generating code in multiple steps. And if you know Verilog, you will know whether the code it has generated would work for you or not. So here is the code which says these are the four inputs, which is very good. This is the dot product, which is also good. These are like your internal registers. They are good. Assign statement is good because I'm assigning outside a procedural block. Name of the variable is dot product, which is actually the dot product. So R0 into B0, R1 into B1, R2 into B2, R3 into B3. That is perfect. And then you have, if a reset comes, you reset all the registers. Otherwise, data in goes to R0, R0 go to R1, R1. I think there's only one change which I want to make it. Make the size of the dot product, that is what the name of, yeah, dot underscore product, dot underscore product as a 32-bit number. So because once you multiply to 16-bit numbers, your result should be, so it has changed the dot product into a 32-bit number. That's very perfect, very perfect. So let's try doing this in here. This is our Copilot, and I'll go to ChatGPT, and I'll go to the very first thing we asked ChatGPT to do was so here. So let me copy this to see how good the ChatGPT does it. Go to ChatGPT. I ask it to, sorry, Copilot to do this for me. So almost the same thing. It has all the output registers. Then at the reset, it is setting all the register to 0. Almost what was done by in the first go was that all the registers, because I think the Copilot also uses ChatGPT 4.0, so it has generated the same kind of code. Let's find out what Gemini would do for us. Okay, so here is Gemini. We can have a new chat, and hey Gemini, let's see how good you are. So good. Almost the same thing. Uh, data in data in goes to R0, R0 go to R1, R1, R2, R2, R3, and then it has assigning it to reg R0, R1, R2, R3. Why it is doing that is, I don't know why. Oh, assigning it to the output. Okay, so it has like 4 outputs. So I can ask it, don't make these registers, make these register internal to the module, and only sum of all the register shall be passed as output to the module. So let's see how good it performs. Perfect, perfect. So Gemini has also done good. Let's see how good this is done by Meta.ai. Oh, I'm in Saudi Arabia, so it is saying it's not available yet in your country. So lucky we are that we have the Meta.ai. So In Saudi Arabia, they don't have Meta.ai. So let's. So, but you can actually try it yourself, and I think it will work. So I've shown you how easy it is to generate RTL Verilog code for a design which you have conceived it right. You know where your registers are, you know the other functionality. So you can very easily generate the design of such a. Uh, so this is so now we understand there are going to be an initial block, which usually is the stimulus, and then the always block. And always block is important, starts with begin and end, and it actually models a digital circuit. And you can have all the behavioral statement in your procedural block. Like initially, you can have your if else statement, your case statements, your loop statements, all inside the block. So if we know if the condition is met, it execute this. If condition is not met, it execute this. So it has to come in an always block where static, and this is the sensitivity. It's a combinational block. This is what you write. N% and star. This means uh, it is a combinational block. Okay, and you use non-blocking procedural assignment, equal, equal, equal. So these are the things which you must remember, that you are saying if select A, then you select A, else if it select B, you select B, otherwise you select C. So there are three values, A, B, and this is, sorry, A, B, and C. If they select B, so you're going to select B. If select A, you are going to select B, otherwise it will be B, otherwise it will be C. So you don't need to think about this, just write a code like this, and preferably like a case statement. A case statement would look like this, a case select, okay? So if 0, 0, it is A, if 0, 1, it is B, if 1, 0, it is C, and default is D or something. So it's a multiplexer. Then there are like some other statement which we don't use a lot, but they are there. Case Z is you put question mark. It means it will only going to check this bit 1. If this bit is 1, answer will be 3. Uh, as don't care. So Z and question mark are the don't care conditions. So it will only check these 2 bits or these 3 bits. So priority encoder, it is going to check if this bit is 1 or the second bit is 1 or the third bit is 1 or fourth bit is 1. It's not going to care about rest of the bits. So you write this code. And it's also going to XYZ, the case X statement, where again, it is going to check only 1 bit or these 2 bits or the 3 bits or the 4 bits to decide about the output. This we have already seen in a forever loop. It says clock is inside an initial block. It says clock is equal to 0 forever. After every 25 time units, you generate a clock. So 0, then it is 1, then it is 0, then it is 1. Every 25 time unit, it'll just switch. And so repeat is something where you say repeat 8 times. So high level language constructs while is also while count is less than 101, count is equal to count plus 1. So all these are very handy, not for the hardware, actually the hardware inferences, but for the writing the stimulus. Okay? The for loop is also there, but you only need to remember once you write a for loop inside a procedural block, okay, it the hardware gets replicated so many number of times. So it's not like software which is running again and again. It is the hardware that gets replicated so many number of times. So it is only a condensed way of writing something very complex, but which will expand and generate a lot of hardware. So we have already covered a synchronous reset is where you don't write reset in the procedural block, rather you write it here. And in an asynchronous, you write these also in the sensitivity list. Okay, and same as the enable, that if enable, then you want to do this. I've talked about the module as well. So let me now go back to where we started with. Let me just cover this a little because I started my lecture by telling you about the digital transformation. And telling you digital transformation does not mean that you just do something in software and you are happy. A true digital transformation is that the digital signature are valued, and that is very important. That you don't have to make people sign uh, digitally with a pen or even digit. So it means that there is a private key, and whenever you affirm your you use your private key to generate a digital signature, it must be valued in law, and it must be valued everywhere, because it is what the uh, it is must always remain confidential to you, your private key. Okay, so if you look at this check, you are sending money to somebody, you write his name here. Okay, in in digitization, this becomes the address of his wallet. Okay, so it is usually the public key which is known to everybody. So everybody can send a check to me by writing my name, or any check to case by writing its name. Why should I hide my name? Because I'm just receiving money. So nobody cares about the is they publish it that pay to a pub key. So we say pay to pub key. So you're paying it to the public key. Right? So this is where your address comes in a digital transaction. And the amount, yes, you have to write how much money that you are going to send it to me. Timestamp is also important, because the date at which you are going to make this transaction. And this is your digital signature, and this is where I would like your pair digital signature, which, as I mentioned earlier, it should be with my private key, which should I keep very close to my heart and nobody should know. And then this is where my money is. If it is a cryptocurrency, it is the ID of a UTXO. If it is my digital currency, it should be my bank account. So that's easy. So this is usually for cryptocurrency or the Bitcoin, we call this is the address of the UTXO index, pay pub key. So here is the transaction. So I need with this signature to redeem some money which is lying in my either crypto wallet or in my bank account. Right? So this is the same, whether it is a crypto money or the real money, but I'm just digitally signing it. So this becomes how the SHA-256. Okay, so this is important. So I write all this transaction, right? I write the complete every information on this check, kind of the timestamp, the amount of money, to whom I am sending, who will get it, this and that. I put it here, make it into a transaction, and generate a hash 256. So if the number of bits are less than 256, I do the zero padding and make them equal to 256 number of bits. Okay, and then what I do is I encrypt them using my private key of the owner, and this makes my digital signature. So this is a digital signature. Okay, instead of affirming this, I take all this information. So this information, like the check is open to public, anybody can see this check. Okay, so the value is not in the text, value is whether the signature is real or not. So you append everything here. If it is a transcript, yes, I assign your transcript here, and case digital signature here, or the digital signature of the vice chancellor here. So I append this digital. Remember, digital signature is nothing, but it is the hash of all the information in the transaction being encrypted using a public private key, asymmetric key encryption. And then I send it on the internet. The receiver receives it. If it may be HEC or a bank or somebody receives it. What it does is that it decrypt my digital signature. So I should get a hash. This is this. But how will it figure out that it has to compute the hash of the transaction? Okay, if somebody has increased or decreased the amount, the hash will change, and we will say signatures are not matching. Somebody has basically muted the transaction because it was just an open. It was going in open, and that's how you make a transaction digitally. But SHA-256 is at the core of everything that happens digitally. So this is how uh, and the Bitcoin transaction is also the same. So if I go, I'll not explain how the Bitcoin works. I so so let me just now try to generate the code that we started with. So okay, so let's have fun uh, with this. Here, okay. So let's have fun with the first. I need a module which should have 8 register. Okay, so I go to any of the tools. So I have no preference at this point. So I have no preference. Let me use this. Okay, so preferably I go and do a new chat. I say generate a module that shall have 8 32-bit registers A, B, C, D, E, F, G, H. Okay, am I right? A, B, C, D, E, F, G, H. At reset, all these registers shall be reset to the following uh, 8 values. Okay, so now I need to write those values. So those values are uh, here. Okay, so I don't have it in the text form, so I say I just write few 8 values. Like I like 0 x 2 e 4 3 2 1 2 3 4 1 b c f 1 2 3 4 5 6 7 8 now. So 1 2 3 4 5 6 7 and 8. So we have 8 numbers. Okay, so to the following, I just say following value, but you can give 8 value. I'm just making it easier. Value at the reset. Otherwise, at every pause edge of the pause edge of the clock, B should be assigned. B should be assigned to. Let's see how is the assignment happening. B should be A should be assigned to B, B to C, C to D. So uh, A should be assigned to B and B to C, C to D, D to E, E to F, F to G, and G to H. And whereas A shall get, I'm just writing sum of all the values in the registers, and also there was another register which was getting something E to F. I should remove this. And also E shall get sum of D and A, for example. Just let's see what it is. Wow. G to H, F to G, E to F. E is D plus A, D to C, C to B, B to A, and A to this. Wow. So it has so easily generated the code, which that at the reset, it reset it to the, I only just being lazy, I was not writing all the 8 values. So all the 8 values gets into this register. Then every pause edge of the clock, Okay, you are getting this. Now there is something else. For example, there are two inputs, two 32-bit inputs, WT and KT. And now I write, change the code so that there are two 32-bit inputs, W and K, inputs W and K, and value of A also add W and K along with rest of the register, rest of the registers. Okay. I wanted to incorporate the two inputs W and K as well. Wow, it's amazing. That's mind blowing, honestly. So it has added these as the input, and because you can see that this is the name of the module, and clock and reset at this wire. Now the two new inputs, so it's a 32-bit W and K new inputs, and these are internal registers, and these are the outputs as well, A, B, C, D, F, because they have got to be output. This is the hash of the design at reset. Uh, this is local param. Remember, local param is something which will not change, and you cannot really call this module and change the local param, which is for your easy, like we do the define. So you do that here, and now these are the shift values, and it is also adding W and K into this. So this is the hardware design of almost, though we need to exactly do this channel, what the channel is doing. This I will leave it to you for the assignment, that you do an assignment where uh, you primarily uh, do do this as well. Okay, so you see that how this whole thing works. कोई question हो किसी का, so you may please ask. But
Sir, Assalamualaikum.
because I've honestly, I'm just doing it once. Do I develop it? But I'm doing it now. It amazes me that how easy it is to just uh, uh, design a chip which has some very complex functionality. Okay, just you break it down into pieces, understand, learn about the architecture, and that's it. So now we know that there is a sensitivity list in case of uh,
Sir, Assalamualaikum. Sir, a question tha regarding the
always
assignment.
block. If you write POSIX clock, it's a sequential logic, and and you always use non-blocking procedural assignment, and do not use a sign. Always block it. Always come outside the always block. So for the combinational logic, this is what you write as a procedural block. Always add this, and you can use all high-level language construct inside, and you can use all high-level language statements. Only you need to make sure that you don't miss any assigning on a variable. You don't miss. Let's say if you have x variable and you are assigning in an if, then you must assign some value on this on y as well. Otherwise, it will assume that you wanted to remember what the value was of x was, what one's condition was true. So it will infer a latch, which is not good. A synthesis tool will usually give you warning. So what I'm saying is that if you are using always static at star, it means it's a combinational logic. Okay. So you say output A is equal to 1, 0, and then if enable is asserted, you are saying do this and okay, but you are not telling what if enable is not asserted, what should be the values. So it will then assume that you want to create a latch which is sequential kind of, which has a memory, which is very bad design. So you must always either have a default value assigned to all your variables. This is the preferred way, a default value. So synthesis tool will assume once enable is not asserted, you want the default value to be assigned. So it will able to figure out that what type of hardware it should do. So this is the preferred way of generating a code. Will this will infer a lag. So you have a default. Combination logic in always block is like this. Add, so select and all the condition. What happens 0, 0, 0, 1, 1, 0, 1, 1 default. So it says these are the values that you generate in case statement. So all high level language constructs will get into the always block. And so there are two types of assignment. If you're using combinational procedural block, you use only equal sign. These are called blocking procedural assignment. On the other hand, if you're using always at pause edge clock or neg edge of reset, then you use non-blocking procedural assignment always. And they happen in parallel. They are not blocking each other. All blocking procedural assignment happen in the order of priority at which you have written them in an always block. So uh, this is where at A, you are saying A goes to this. So it's a non-blocking procedural assignment. They happen at the same time. Okay, usually they are the registers. And here, once you say A is first this and then B is equal to A. So in this case, both will happen in parallel. So B will have something which it already has. It will not be this because this is not happening in a sequential manner. Okay, it's not happening in a sequential manner. But this blocking procedural assignment will block this to happen unless this would happen. So this is basically combinational logic that you assign these statements to. So this is an example that you put star instead of adding all in your sensitive list, or clock will have the pause edge of clock or neg edge of a reset. So uh, so this is we have already seen a predictor working. This is the code that I have generated, and we have seen it all. And I was talking to you about the digital payment. And yeah, so this is important. Trade-off in design is why even you worry about the architecture. It is almost the same as is the architecture of a house, that you have a limited area. Once you're designing, because you got to go and buy a piece of land, okay, so you area becomes very precious because you only have finite area. And area is proportional to the cost, especially if they are FPGAs. A smaller FPGA will cost you less money, a bigger FPGA will cost you a lot more money. So it directly translates into the cost in dollars. The second important thing is the speed, because you want it to be run faster and faster, which is a more capable circuit. So you want to clock your design at a very, very high rate. Then energy is an issue, because once you're clocking it fast, you dissipate more energy. Sometimes you don't care because all you care is the power. So all these GPUs and all these high performance computing, they care less about power. So they have special cooling strategies to cool out the hardware. But in the mobile devices like my mobile phone, you are also worried about the power dissipation. You want your design to the device to live forever. In some case, like IoTs, you want them to remain alive for years, if not months. Okay? So these are all competing design objectives. All competing design objectives. So so that's why there is a competition, and you try to find out the sweet spot where you get the best design trade-off based on what you are into. Timing, circuit timing is uh, depends upon how fast you want to clock your circuit. Okay, faster, too fast, and so the timing closure, you need to see that how you do a timing closure on the design. Let me just take this out. I think the battery will die soon if I don't plug it So the second thing you need to know why the timings are important, because though the simulator will not able to figure out that there is a delay in the logic that you have put in, because simulator will simultaneously, if you it's an inverter and you have a 1, the inverter will change it to 0. If you switch it to 0, it's right there at it's because it has no way of figuring out the delays, because delay is a function of technology. Let me see if I plug this into a power. Okay, so what actually happens is that once a transistor is switching from 0 to 1, so there are like a real delay into which is not right away. The transistor will switch, and this delay basically every gate that a signal passes is switching. Every transistor will cause a little delay into switching from 0 to 1 or 1 to 0. And once you accumulate these delays, in a path, so this is an actual real inverter delay. So it was 0, and then once you're switching it to 1, and this is like where we say it gets to 1, and this was 1, so we say here it will switch to 0. So this is the delay, and this delay is some real delay depending upon the technology, and that is something which you need to worry about. And this is the delay, and because of the capacitance and resistance, whatever that means, uh, you just think that actual physical circuit, and once a signal is passing through the transistors, they will cause a delay, and you need to worry about that delay. And that is where putting a lot of combinational logic into the functionality. Just remember this, a lot of combinational logic, like I was counting the number of comparators, and as they were increasing, so means the signal going from one comparator to another, to another, to another, to another, to another, that will cause a lot of delay, and that will limit that how fast can I switch or clock my design. So if as I cannot clock it faster, then it is a very poor design. So we need to worry about the combinational logic we are putting into our design. So all these delays would, and why there are delays, this is important. Yeah, so you see that this is a logic, this path is going through, and that's why I told you trace all the paths. So there's a path which is going to only one comparator, then a path which was going to across two comparators, then three comparators. So the path which is only going through one comparator or one gate delay, it will have some value, stable value, but the second value is coming from here. This is the second path. So this value, based on this value, and this value, whatever was there, will switch. And then comes the longest delay, man, because which is going to define the final value of the output. Unless you don't have this and this or, you cannot really figure out what this and would say. So there will be some transition like this, and is shown here. with this. So this is where the transitions are happening. Sometimes the signal is going to 1 to 0 to 1 to 0 before it gets stable. And that is the longest path will define that when the signal gets stable. And that longest path is the path which you should worry about. And once you are doing synthesis, the synthesis tool will tell you that what is which one is your critical path, and that critical path which is called the longest path in your design, okay, which has a cumulative delays of two in two AND gates and one OR gates. Okay, so there's two AND gates and one OR gates. This is the longest path, and the shortest path is only this AND gate. Okay, so that will define that how fast you will able to switch. So we need to worry about these things because once you're designing, it is always a good idea to keep on synthesizing, design, synthesize, so that ultimately you will be given a target clock. First, you should know in your mind that how you're going to break down the cloud functionality, the combinational cloud functionality, to ensure that there are no very long critical path in your design. But your the part that we are doing, RTL Verilog code in a simulator, will only give you the functional correctness of the code, not the timing. Timing would only come once you physically synthesize the design. So this is only the functionality, that whether functionally your design is correct or not. Okay, so functionality. So for that, to check the functionality, you write a test bench. Okay, in a test bench, you have a test bench module which we have just seen. A test bench module which has no input and output. Test bench has no input and outputs. It instantiates a device under test. This is something which you want to test. So the device under test has certain inputs. So these are the inputs which you derive from here. So this is a test pattern generator. This is where you got to be very creative. That how you generate. Uh, are you going to manually generate all the test patterns, or you are going to automatically generate all the test patterns? And then output, are you manually going to check each and every output to see whether you are getting correct answer or not, or you may have some way to automate them? So test bench provides input test patterns to the device under test. They may be handcrafted values. To start with, for your initial design, you do the handcraft. Okay, so you do the handcrafting, and once you're happy, then you say, now I want to really test it rigorously uh, using some other ways, or then you do rigorous testing of this, or you automatically generate. As I told you, that verification engineers are very valuable. There's a lot of jobs for verification engineers because people want to make sure that, and the design tools will also tell that how good a coverage a specific verification engineer has actually done to the design. So and they are paid well as well. But a real fun, though, is also in verification, but real fun obviously is in doing the architecture design. So so is the outputs. They can be handcrafted values which you see whether you're getting those outputs or not. And sometimes you may have a golden design. So a device under test, for example, I'm doing hash. So hash is also available in Python, for example, hash function. So I say, instead of saying and looking at whether I'm getting correct answer or not, I have a module, something which a software that is the golden design, and I give the same input to this and then check automatically. So I'm just generating automatically a lot of random data, humongous amount of random data, passing it to both the my golden, which is the Python code, and this, and then I compare. So these are the techniques which are used. As the test bench can be an HDL code, a circuit schematic also. Once you have synthesized, again you want to test it, as I mentioned earlier. So So test bench is not designed for hardware synthesis. It is only to check the functionality. It runs in simulation only. So it is only to test how good your design is. Only you are simulating. So 4 ways. One is your input outputs are manual, your error checking is manual. This is the first step. You start by doing this. Once you have some initial design done, then you may want your self-checking to be manual, and automatically it is checking. So you have a golden design, and then it is just checking whether. And then comes a thorough, where you just put billions of inputs and outputs, and you let it run for days. And you say you have designed an environment. It's a pretty complex design, which would take it many days to actually run it. And wherever there's an error, it should just start logging that for this input, this is the wrong output, this input is the wrong output. And you have a log file, and log file should tell you that how many mismatches you are getting. Okay. So I think this is pretty much I wanted to do today. Uh, Let me ask you if you have any specific questions